students, we have started with the atomic models. In our previous class, we have discussed about Thomson's atomic model and Rutherford's atomic model, along with their drawbacks. To remove the drawbacks in the Rutherford's model, combining some basic laws of classical physics and some principles of quantum theory, Niels Bohr proposed in 1913 his famous atomic model, which successfully explained the different properties of atom, such as stability of atoms, spectral characteristics of the atoms, etc. Because of this contribution, Bohr was awarded Nobel Prize in 1922. As a prelude to this Bohr's theory, we should have an introduction to nature of radiations, number 2, atomic spectra, and number 3, quantum theory. We know that ordinary light, X-rays, gamma rays, etc. are called electromagnetic radiations, and they have wave characteristics. These radiations are called electromagnetic because when they pass through a point in space, they produce oscillating electric and magnetic fields at that point. In 1873, a Scottish physicist, James Clerk Maxwell, called this radiation as electromagnetic waves or electromagnetic radiations because they were associated with both electric and magnetic fields. This gave birth to a new theory known as wave theory of light. Now let us see some of the characteristics of this wave theory of light. The first point is that the light is transmitted in the form of electromagnetic waves. Secondly, the electromagnetic waves are associated with electric and magnetic waves directed at right angles to each other and also perpendicular to the direction of propagation of the wave. Thirdly, all electromagnetic waves travel with the same velocity, which is equal to the velocity of light. The fourth point is that electromagnetic waves do not require any medium for their transmission or propagation. Some of the examples of electromagnetic radiations are gamma rays, X-rays, UV rays, visible light, infrared radiation, microwaves, etc. And all these waves, they propagate in the form of electromagnetic wave. Now, a wave is characterized by the following parameters: wavelength, frequency, velocity, and wave number. Let us first discuss wavelength. Consider a wave profile as shown in this figure. The distance between two consecutive crests or two consecutive troughs is termed as wavelength. It is measured in centimeter or in angstrom. We know that 1 angstrom is equal to 10 to the power minus 8 centimeter or 10 to the power minus 10 meter. Our second fundamental characteristic of a wave is the frequency. Now, what is frequency? Frequency is the number of waves passing through a given point in 1 second. And frequency is expressed in cycles per second or hertz. The third one is velocity. Velocity is the distance traveled by a wave in 1 second. Velocity is equal to distance traveled in a wavelength divided by time taken to travel one wavelength. Now this is the relation between speed of light, wavelength and frequency. Now C is equal to mu lambda. So write this equation. C is equal to nu lambda. In spectroscopic work, a term called wave number is often used. Wave number is denoted by nu bar. So what is this wave number? Wave number is a number of waves accommodated in unit length, or it can be defined as a number of wavelengths per unit length. Wave number is equal to 1 by wavelength. That means wave number is the reciprocal of wavelength. So nu bar is equal to 1 by wavelength, that is 1 by lambda. Now from this equation we can see that lambda is equal to C divided by nu. So 1 by lambda is equal to 1 by C divided by nu. That means this nu will go to the numerator. So nu bar, that is wave number, is equal to nu by C, or wave number is equal to frequency divided by velocity of light. Now let us discuss about atomic spectra. When white light is passed through a prism, it is separated into light of 7 colors: VIBGYOR, violet, indigo, blue, green, yellow, orange and red. Now these are radiations of different wavelengths. The pattern obtained by splitting or sorting out radiations into component wavelength is called a spectrum. The spectrum of white light, when analyzed by spectrometer. What is a spectrometer? It is an instrument that indicates the wavelength or frequencies of individual components of a radiation. So, the spectrum of white light, when analyzed by a spectrometer, is a continuous spectrum, suggesting that white light is made up of all possible wavelengths or frequencies of radiations. If a gas is heated, it emits light. When this emitted light is analyzed in a spectrometer, the spectra obtained consist of a series of well-defined sharp lines, each line corresponding to a definite wavelength or frequency. These line spectra are characteristics of atoms. So what is atomic spectrum? The spectrum obtained on account of the characteristics or behavior of an individual atom is called atomic spectrum. The atomic spectrum consists of sharp, well-defined light corresponding to definite frequencies. The atomic spectra are of 2 types: emission spectra and absorption spectra. Now let us discuss quantum theory of radiation. According to this theory, a body cannot emit or absorb energy in the form of radiation of continuous energy. Radiant energy is emitted or absorbed discontinuously in the form of small energy bundles or energy packets known as quanta or photons. This implies that radiations obtained from excited atoms consist of a stream of photons and not continuous waves. Now, each quantum of radiation is associated with a definite amount of energy depending upon the frequency of radiation. The energy E of a quantum is given by E is equal to h nu, where h is known as the Planck's constant, whose value is 6.626 into 10 to the power minus 27 arc second. What is this nu? This nu is the frequency of radiation. Now this energy E is equal to h nu is equal to h c by lambda, because we know that mu is equal to c by lambda, is equal to h c into 1 by lambda. Now what is this 1 by lambda? 1 by lambda is nu bar or wave number. So E is equal to h c nu bar. Now a body can emit or absorb energy only in an integral or whole number multiple of quantum. Thus, radiant energy can be absorbed or emitted as h nu or 2h nu, 3h nu, 4h nu, 5h nu, etc. But this energy can never be absorbed or emitted in fractions of quantum, that is 1.6h nu, 1.3h nu, 3.2h nu, etc.